homework problem number 2 from homework 2. What is the strength and direction of the electric field at position indicated by the dot in figure 26.2? Identify the direction as an angle below the horizontal line. So we know that the equation for finding the electric field of a position from source charges is E is equal to the constant K times the charge over the radius. So what do we have? We have our Q1 at 3 nanocoulombs. So Q1 is equal to 3.0 nanocoulombs. Q2 is also equal to 3 nanocoulombs. Then our R, we have R1 is equal to 5 centimeters, and R2 is equal to 10 centimeters. So before we plug in anything, we want to know what the electric field would look like on the particle. So what would be the electric field on the particle coming from Q1? It's horizontal, so it is pushing, and we know the positive charges push particles outward. So here we have our electric field from Q1. Now our Q2 is coming in from a diagonal, and so it's also pushing it out, so we have an electric field coming out here. Now our net electric field will be the sum of these both. So our electric field will be somewhere in the middle here. Sorry, it's a little squished. So we also, because we have a diagonal, we also need to know what this angle is right here. So we can look at that by looking at our radiuses of 10 and 5 centimeters. We can do the tangent of our angle is equal to 10 centimeters over 5 centimeters. And if you plug that into your calculator, that gives you 63.43 degrees. Then, so this is our angle. Now we can go back and solve for our electric field from Q1 as it's horizontal, so it's only pushing in the horizontal direction, and we can solve with the I. So we have E1 is equal to K times 3 nanocoulombs over, but we can even, to like save ourselves energy now, we know that 3 nanocoulombs is the same as 3 times 10, my pen's running out of ink, 10 to the negative 9th coulombs. Is that, can you still see that? Okay. Over R1, which is 5 centimeters, which you can narrow down even further to 0.05 centimeters. And if you plug and chug, as Dr. Bailey says, you get 9 times 10 to the 9th times 3 times 10 to the negative 9th over 0.05, and that leads you to an electric field of 10,800 in the I direction, the X direction, also known as I, newtons per coulomb. Right, that's easy, right? Well, now we get to do the hard part. We get to do the electric field of the diagonal force, which is going to start off the same with the 9 times 10 the 9th times 3 times 10 to the negative 9th, but this time over 10 centimeters. Wait, not over 10 centimeters. It's Pythagorean theorem, so we have it's over 5 squared plus 10 squared centimeters. And then we multiply that by the angle, which was 63.43 degrees, the cosine of that, I'm sorry. The cosine of this, I, plus the sine of 63.43 degrees. And I'm gonna go to the next piece of paper. So from there, we can plug and chug and we get 966 in the I direction, so in the X direction, plus 1,932 newtons per coulomb. And then from here, we want to do the E net. And to remind everyone, I'm going to change colors. The E net is equal to E1 plus E2, and then E1 is equal to the E in the X direction plus E in the Y direction, but we know there is no Y direction there. So, and then we have E2 is equal to EX plus EY. So our E net is equal to 10,800 I plus 966 I. Just double check to make sure. Yeah. And then plus our 1,932 J, which leads us to 11,766 I plus 1932 J newtons per coulomb. So that is our electric field on our point here, our point charge from back up there. This is our E net. Now, to know about the angle above the horizontal, which was here, we want to use, again, the tangent function of our angle, which is this, is equal to our y, which is our 1932, over our x, which is our 11,766. That leads us to an angle of approximately 9.3 degrees above horizontal. Another thing about E net is we can't have it separated like this, so we're gonna do a square root where we do E net is equal to the square root of, here, I'm gonna change the colors once again, of 11,766 newtons per coulomb squared plus 1932 newtons per coulomb squared, and that is equal to approximately 12,000 newtons per coulomb. And there you have it.